Chapter 2. This is the second of 13 chapters that we will do in this course. Chapter 2 marks our start in the world of logic. This entire course actually features a lot about logic, and it forces you to really think about things a little bit differently. In 2.1, we're going to be focusing on inductive reasoning. Inductive reasoning is going to help us make observations about patterns that are occurring in sequences, as well as being able to look at some data points and draw some conclusions. But first, inductive reasoning, it's the reasoning that we're using based upon the observations we see in our patterns. So in our very first example, yep, we're already ready for one. It says we're going to look for a pattern and we're going to decide what the next two terms are in this sequence. When I see the sequence 3, 9, 27, 81, I'm trying to figure out, okay, well, how is somebody getting from 3 to 9? Okay, well, I'm adding 6, but then I go from 9 to 27 and I'm not adding 6. It's not some consistent value. So maybe I'll try something different. Okay, maybe 3 times 3. All right, well, 3 times 3 is 9, and 9 times 3 is 27. Aha! I think we figured out the mystery. To get from term to term, I am multiplying by 3. So to continue on with that process, all I need to do is multiply 81 by 3. And when I do 81 multiplied by 3, I get 243. When I take 243 and multiply that by 3, I get 729. Okay? So we observed here that the pattern is multiplying by 3. I want to point this out as something that might be helpful in the future. If I ask for you to find, I don't know, the 20th term in the sequence, I doubt any of you would really want to continue to multiply by 3. One of the things we do in math is we create equations. Okay? Something that could be helpful to create an equation is looking at what we call an n value, where n is the location of the term in the sequence. Okay? So looking at this term here, 243, because 243 is the 5th term of the sequence, my n value is 5. Okay? How could I use an n value when creating the equation of a sequence? Well, we saw that we were multiplying by 3, okay? But how would I get that first term? If I take 3 and raise it to the power of n, let's try that, okay? 3 to the first power is equal to 3. This corresponds with my very first term, which has an n value of 1, producing a term of 3. If we do that with our term that we just solved for, 3 to the 5th power, 3 to the 5th power is equal to 243. So you could look at this as an exponential relationship, which later on you'll discover in your math career is what's creating the multiplied by 3 component. All right, now we have some circles. We have 3 circles, and we need to draw a conclusion about what the next 2 terms are in the sequence. And when I'm looking at these terms, I'm trying to make observations about what's different. I see that in this sequence, all of my terms are apparently going to contain a circle. Okay? So I'm going to create 2 circles for our next 2 terms that we need. All right, there's one of them, and here's going to be another one. All right, so no matter what, we know we're going to have circles. But the main difference I'm seeing in these figures is the shape that is located on the inside of each figure. I'm noticing that our very first term has a triangle. Triangles have 3 sides. Our second figure has a square. Square has 4 sides. The third term has a pentagon. Pentagons have 5 sides. So looking at the number of sides, I'm going to use the number of sides to help me determine the next 2 terms. Because my first term has 3 sides, my second term is 4, my third one has 5, I'm going to bet that my next term has 6 sides. All right, let's see how good I am at drawing these things. All right, so if my fourth term has 6 sides, then I'm going to draw the conclusion that I bet you this 5th term has 7 sides. All right, this one's going to be rough. 1, 2, 3, 4, 5, 6, 7. All right, it's not perfect, okay? If I want to create an equation, I'm noticing that my first term here is 3, and I'm noticing that this guy here is 4, all right? If I want to relate them to their n value, the n value is 1, the n value is 2, so maybe if I create the equation n plus 2, that would tell us the number of sides each term will have. All right, sorry that was a little bit slow, but let's see if that helps you figure out the next two guidance. You have 2 different sequences. Please answer them now in your Edpuzzle and in your notes. All right, let's see if you got them right, and if you did not, try to check your work here. All right, well, what we were just doing is we are creating conjectures. Conjectures are those conclusions that we can reach using inductive reasoning. You just created conjectures by determining what the next 2 terms were in a sequence. All right, so then we are looking at these circles, and we need to create a conjecture about what we can determine will happen when we use 20 diameters in a circle, okay? This is where I was referring to on the previous page that might be helpful to create an equation, okay? Looking at the first term, I'm noticing that there are 2 regions formed by 1 diameter. There are 4 regions formed from 2 diameters. There are 6 regions formed by 3 diameters. And I'm looking at the number of regions because that's actually where I was directed to look in this example here, okay? How does the number of regions correlate to the number of diameters, okay? The very first term in the sequence has an n value of 1, which corresponds actually to the fact that it only has 1 diameter, okay? The second one has an n value of 2, it's the second term in my sequence, which correlates to the fact that it has 2 diameters. How can I relate their n value to the number of regions formed in each situation, okay? Well, I'm noticing that 1 times 2 is 2, 2 times 2 is 4, if I throw this one in here. This one has an n value of 3, 3 times 2 is 6, getting me an equation of n times 2, okay? Where once again, that n value in this scenario is relating the number of diameters as well as where it is in the sequence, okay? That equation is going to help us figure out how many regions there will be when 20 diameters is used. So we have 20 diameters. If I multiply that by 2, I get 40. So the conjecture that I am making is that if we were to draw 20 diameters, 40 regions would be formed. All right, here's your term. What conjecture can you make about the 21st term in this pattern? All right, let's see. According to the answer, every third term is B, so the 21st term has to be B, okay? One of the ways I could figure this out, okay, because B is appearing as the third term every situation, it's important to notice that 21 is divisible by 3, which is why it's going to spread out evenly over the course of this sequence. All right, it's a little bit harder. These are a bit more difficult examples, so fair warning, example 3's got it, could be tricky. All right, what conjecture can you make about the sum of the first 30 even terms, okay? All right, well, even numbers. So the first even number is 2, okay? That's going to be my first term in the sequence, 2. My second term in the sequence, I'm going to find the sum of 2 plus 4, and that gets me 6, okay? So I'm looking at these sums. The third term is 2 plus 4 plus 6, and that gets me 12, okay? So forth and so on. I'm just looking at these first 3 to figure out, can I use these terms and their locations to create an equation, okay? All right, so 2 was the first term, 6 is the second term, 12 is the third term, okay? Let's see. So the first term has an n value of 1. We know Okay, well 1 times 2 gets me 2. All right? Well, the second term has an end value of 2. 2 times 3, that gets me 6. All right, well, so far I'm not seeing a ton of consistency here, but let's keep trying. Let's go a little bit further. 12 is the third term of the sequence. Well, 3 times 4 is 12. Notice, okay, so here's an end value. And whatever I'm multiplying by always appears to increase 1. 1 more than that end value, okay? That might take a little bit of trial and error. So now I'm going to create the equation that we have n, which is our location in the sequence, multiplying that by n plus 1. So because I'm trying to find the sum of the first 30 even numbers, that'll be located at the 30th location in my sequence. So I'm going to do 30 times 30 plus 1. And when I do 30 times 30 plus 1, I get 930. So my conjecture is that the sum of the first 30 even numbers is going to be 930. Okay? All right, yours is tricky. Fair warning, it's a challenge. What conjecture can you make about the sum of the first 30 odd numbers? Try using the strategy we just did above, where we list out the terms and we try to create an equation relating it to its n value. All right, so I'm hoping that you found that the sum of the first 30 odd numbers is 900. And we get that by understanding that all you need to see is that the location n, when you square that, it gets you the sum. All right, we're going to keep going. I'm almost there. In this next example, I think you've probably seen something similar to this before when you draw conclusions based upon what you see in a picture. So sales of backpacks at a nationwide company decreased over a period of 6 consecutive months. What conjecture can you make about the number of backpacks the company is going to sell in May? So I'm looking at the data points that I have, and I'm noticing that, all right, well, it appears that they're trending down. Okay, why a company's backpacks are trending down, maybe you can make a good assumption, all right? I'm going to use the slope of some of these last 2 data points, okay? And approximately, this is all approximate here, it looks like we're decreasing by approximately 500, maybe, okay? So then I'm going to say that potentially, maybe, just an estimate here, maybe the company will sell about 8,000 backpacks. 8,000 backpacks sold in May. Okay? But what you for sure can concretely draw a conclusion is the amount will for sure be less than April. The amount sold will be less than April. And I'm drawing this conclusion because I'm noticing that my data points are trending down. All right, you have 2 little checks to do. I want you to draw a conjecture about the backpack sales in June, and I want to answer the question, is it reasonable to use this graph to make a conjecture about August? Explain. All right, so I'm estimating that if we continue to trend downward, there'll probably be about 7,500 backpacks sold. And because it's a backpack company and your kids need backpacks to go to school, I don't think I would use this graph personally. Last page, last example. What is a counterexample? A counterexample is something that I use to prove to you that your conjecture is incorrect, okay? It is an example. So here we go. We need to find a counterexample for each of these conjectures. In example A, it says, if the name of a month starts with the letter J, it has to be a summer month. So what my job is to find out a counterexample is I need to think about a month starting with the letter J that is not a summer month. I want to disprove something, okay? Because in the summer we have June and July for sure. Well, a month that starts with the letter J and is not summer, I would say is January. That's when Miss Rudolph gets married. You'll be thanking me as I'm freezing my tushy off. All right, let's go on to example B. You can connect any 3 points to form a triangle. So what this is saying is any 3 points that I draw, no matter what, I can connect and create a triangle. Well, is there any way for me to rearrange the locations of these 3 points so that they don't form a triangle? What if I take them and create a straight line that goes through all 3 of these points? These 3 points would then be considered collinear because they form a line, and the line is not a triangle. All right, question C. Oh boy. When you multiply a number by 2, the product is greater than the original number. So what I need to do is I need to find a number that when I multiply it by 2, whatever it produces cannot be greater than itself, okay? We don't want it to be greater than itself. All right, so let's think of some numbers. What if I multiply by 2, okay? If I plug in 2, 2 times 2 is 4. Is 4 greater than 2? Well, that wouldn't be a very good counterexample because I did not just disprove the statement. All right, well, let's try a different number. Let's try, how about 0? 0 times 2, well, that gets me 0. Is 0 greater than the number itself? No, that's not true because they're equal to one another. So the counterexample I would use is 0. All right, last got it, and then we're finished with our notes. Check your answers. Obviously, when you're finding counterexamples, there's many correct answers. All right, I'll see you tomorrow.